presented by Group 12 Sam Ratalungi University, Generating Functions, Recursion, and Recurrence Relations. Our team, Naomi Wehantouw, NIM 241011060019, Michelia Sonambela, NIM 241011060039, Marvan Syamsuri, NIM 241011060080, Natazia Dhea, NIM 241011030025, Syallom Emor, NIM 241011030018. Lecturer Christy E. JC Montalalu, S.C. MSc 1985-1210-2008122001.
Background in discrete mathematics, understanding patterns and relationships between elements is essential for solving various problems, both theoretical and practical, especially in computer science. One common form of pattern is numerical sequences, which often cannot be explained by a simple, explicit formula, but require a more structured or iterative approach. This is where recurrence relations play a key role, describing how each term in a sequence relates to its predecessors. Meanwhile, recursive functions allow us to compute each value step by step, based on prior results. Generating functions serve as a powerful analytical tool, representing entire sequences in algebraic form. These three concepts are deeply interconnected and form a strong foundation for combinatorial analysis, algorithm design, and the development of efficient, systematic problem-solving strategies. Generating functions. Definition. A generating function is a formal power series in which the coefficients represent the terms of a sequence. It is used as a tool to solve counting and reoccurrence problems in combinatorics. Formula. A generating function is a mathematical tool that expresses a sequence of numbers as a power series in a variable, usually x. In this function, each coefficient and a nan represents the value of the nnth term in the sequence. Generating functions are widely used in solving combinatorics problems, recurrence relations, partition problems, and discovering patterns in sequences.
Simple example of generating function. Suppose we have an infinite sequence where every term is 1, 1, 1, 1. The generating function for this sequence is, this is a geometric series, and it simplifies to the formula. This is one of the most basic and commonly used forms of generating functions in combinatorics.
Applications in combinatorics. Generating functions are powerful tools in combinatorics. They allow us to count combinations and subsets efficiently, solve recurrence relations with precision, and explore integer partition problems. For example, how many ways we can express a number as a sum of other numbers. These functions are also widely used in computer science to model counting problems in algorithms and data structures.
Recursion. Definition. Recursion is a technique in programming where a function calls itself to solve a problem. In this context, a recursive function breaks down a complex problem into smaller, similar subproblems until it reaches a base case that can be solved without further calls. Two main components of recursion: base case, the condition to stop recursion; recursive case, the part where the function calls itself.
Chapter: Factorial. Factorial is one of the most basic and commonly used examples of recursion in programming. In recursion, factorial can be defined as if n equals 0, return the value 1 because 0 exclamation equals 1. If not, the function calls itself with n-1 and multiplies the result by n. This process continues until it reaches the base case n equals 0. Example: Fibonacci sequence. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding ones. In this concept, the Fibonacci series can be written as if n equals 0, return 0. If n equals 1, return 1. If n greater 1, the function calls itself twice, Fibonacci n minus 1 plus Fibonacci n minus 2, following the Fibonacci formula, f of n equals f of n minus 1 plus f of n minus 2. The function keeps calling itself until it reaches the base cases, n equals 0 or n equals 1. Example: Binary search. In binary search, the sorted data is divided in half, and if the target value is not found in the middle, the search continues in the appropriate half. The base case is when the low index is greater than the high index, which means the target value is not present in the array.
Recurrence relation definition. A recurrence relation is an equation that defines each term of a sequence as a function of one or more of its preceding terms. Common example. This means that to find the nth term, we use the value of the n-1th term and add a constant. Types of recurrence relations: homogeneous, non-homogeneous. Goal: to find a closed-form solution, that is, an explicit formula for the nth term of the sequence, solving recurrence relations. Iteration: repeated substitution. Example: substitute step by step. A1 equals A0 plus 3 equals 2 plus 3 equals 5. A2 equals A1 plus 3 equals 5 plus 3 equals 8. A3 equals A2 plus 3 equals 8 plus 3 equals 11. Pattern: n equals 2 plus 3n. Closed form. Characteristic equation for homogeneous relations. Example: this is a geometric sequence. The general solution, closed form, generating function. Example, sequence, n equals 1 for all n generating function. The coefficient of x to the n is one constant sequence. Closed form.
Connecting the three concepts. The three concepts, recurrence relations, recursion, and generating functions, are closely related in solving problems in discrete mathematics. Recurrence relations are used to describe patterns between terms in a sequence. Recursion is a method of calculating values based on previous terms, often applied in algorithms. Meanwhile, generating functions are analytical tools that help find closed-form expressions or efficiently count the number of possibilities. Short example: by understanding all three, we can build models, perform computations, and carry out comprehensive analysis. Conclusion. In conclusion, generating functions, recursion, and recurrence relations are three interconnected tools that play a vital role in solving problems in discrete mathematics. Recurrence relations provide a structural model of how each term in a sequence relates to its predecessors. Recursive methods allow for step-by-step computation of these terms, making them useful in both mathematical reasoning and algorithmic design. Generating functions offer a powerful analytical approach to derive closed-form expressions and count combinatorial possibilities. When used together, these concepts allow us to model, compute, and analyze mathematical patterns efficiently and systematically. Thank you for your attention.